Now let's move on to the study of heteroscedasticity. In this part, we're mainly going to look at 4 questions. The first one is, what is the problem of heteroscedasticity? What does it mean? Secondly, what are the possible consequences of heteroscedasticity? Third, how do we test or how can we detect the problem of heteroscedasticity? And fourth, if we know there's a problem of heteroscedasticity, how do we solve the problem? Okay, so first of all, what is the definition of heteroscedasticity? We know that there are a few assumptions behind least square estimations, a number of them, and heteroscedasticity is related to the third assumption behind least square estimation. So basically, the problem is the following. So the third assumption of least square estimation is that the variance of y, or the variance of the error term, should be constant for all different observation unit, and it should be equal to something like sigma square. It's a constant. And heteroscedasticity refers to the case that this assumption is violated, in the sense that the variation of y, or the variation of the error term, is not a constant anymore, but can be potentially different for different observation unit. And when there's a problem of heteroscedasticity, the consequence is that the least square estimator is still linear and unbiased, but it's not blue anymore. It's not the most efficient one among the unbiased one anymore. And secondly, the test statistics, so the t-test, so on, the test statistics on the coefficients are not correct anymore. Okay, so to some extent, you could also say that heteroscedasticity is less as big as a problem compared to omitted variable, because when you have omitted variable, your estimator is actually biased, so you just get a wrong parameter. So for heteroscedasticity, you still get somehow unbiased estimator. The only thing is that it's not efficient. Okay, and if you want to solve or address the problem of heteroscedasticity, there are mainly two ways you can go. First is you can transform the model to get homoscedastic errors if the error source of the problem is known. So in this case, you can do this via weighted least square. And secondly, you could also apply wide heteroscedasticity corrected standard error, and in this case, it's not going to solve the problem. So basically, it's not going to solve the problem that the estimator is not blue, but at least it will give you the right test statistics for t-test and so on. Okay. All right. First, how to detect heteroscedasticity. Okay, there are two ways of doing that. One is what we call informal test. You can just do a residual plot. So basically, you plot the residuals over the number of observations and see whether there's a clear pattern that it doesn't seem to have a constant mean. And second way is that you can do a formal test, which is called Lagrangian multiplier or LM test. And for heteroscedasticity, the most commonly used one will be the white test. All right. So let's first look at how we do the test informally. Okay. So basically, what you can do in this case is that when you run a regression, you can just plot the residual against any independent variables and see whether it appears that the residuals have a constant mean. But let's say for the situation in this graph, what we can see is that for sure, while it appears that the mean of the residual is more or less around zero, but the fluctuation, the amplitude of the fluctuation of the residual tend to be bigger when the income is changing. So basically, it's very likely that the error term actually depends on the dependent variable income. And in this case, it's surely an indication that you don't have constant variance and you have the problem of heteroscedasticity. Okay. And how do we do that formally? Okay, so here is the way that we can do. So basically, after you run a multiple regression, just like the standard multiple regression, what you can do is that you calculate the variance of y, or you calculate the variance of the residual term. Okay, you have the estimated residual, you make a square for it, and then you run the residual on the list of other variables and see whether those other variables have explanatory power of the square residual. Okay, so the null hypothesis will be that the coefficients for all other variables should be 0 because the residual term should have a constant mean, should be constant over time. So in general, if the assumption of constant variance is true, so basically the variance should be, squared error should just be a constant and it doesn't depend on anything. Okay, so then the null hypothesis will be that all the coefficients for other variables is just 0. And the alternative hypothesis is, of course, at least one of the coefficients is not 0. Okay, and how do we calculate the test statistics? So basically, here is what we can do. So when we do the estimation, okay, it's just a linear regression with the square error as a dependent variable. And in this case, the larger the R-square is, the more likely that the square error can be explained by at least one of the independent variables. And the more likely that the square error can be explained by other variables, then the more likely that the square error is not a constant. And then the larger the R-square, the less likely that the square error has a constant mean or is a constant over observations, and the less likely that you are going to have homoscedasticity. Okay, so this is how we do the test. Okay, the test statistics will be n. N is the number of observations, so test statistics will be n times R-square. And these test statistics should follow a chi-square distribution with s minus 1, so the number of coefficients here, s minus 1 degrees of freedom. Okay, and in this case, note that high R-square provide evidence against a null. So basically, the null hypothesis is there is no heteroscedasticity. And if you reject the null, that's something saying that you probably have the problem of heteroscedasticity. And also, it's a chi-square test, so it's a one-sided test in this case. Okay, it's on one tail. So you just need to look for the 95 percentile of the distribution, and you don't need to translate into like 97.5 percentile or 2.5 percentile. All right? Okay. Or actually, since it's a kind of a test of joint hypothesis of a linear regression, actually you can do the same thing using an F-test. But since it's just much easier to calculate the test statistics in a chi-square test, so basically, I think you should have no problem doing it with F-test, but I will only require you to be able to do the chi-square test instead of the F-test. Okay, so and here is the kind of how we can do the thing practically. So when we want to do the estimation of the square error on other explanatory variables, how to find those variables is actually quite tricky if you don't know the true data generating process of the error term. So a very plausible suggestion will be that we just use the independent variable x's as the variables for z. Okay, and in this case, it's simply that we regress the square error on all the independent variables and see whether the square error is correlated with all the independent variables. And if the correlation is strong, that's an indication for heteroscedasticity. Okay, so basically, again, just to repeat, the null hypothesis of y-test heteroscedasticity test is that there's no heteroscedasticity. And suppose you reject the null, suppose the p-value of the test is less than 0.05, or the chi-square statistics is larger than 95 percentile critical level, then that's an indication you have the problem of heteroscedasticity. Okay, if you want to do that in eViews, you can just look at the output table of the regression. You go for view, you go for residual test, and then you search for wide heteroscedasticity test. For simplicity, you can just go for no cross terms. And if you do that, the eViews is going to report for you something like, okay, so this is the result table you have. They report for you both the result for F-test and the chi-square test. You should know that this obs means number of observations, so just n. So you should know that this n times r square is just the test statistic you should use for the chi-square test. So it's n times r square. In this case, it's 500 something. Okay. From eViews, you can read the p-value directly, and this p-value tells you that you reject a null. So there is a problem. But if you want to do the test formally, you should compare this nr square with the critical level of the chi-square test. And in this case, you can find the critical level of chi-square by using scalar chi-square is equal to you just search for the 95 percentile of chi-square distribution with 2 degrees of freedom. So it's here, if you search for 2 x variables here directly for you, okay, so just search for 2, and it tells you that the critical chi-square will be equal to 5.99. Clearly 500 is larger than 5.99. So that also leads to the same conclusion that you reject a null hypothesis of no heteroscedasticity, and the test result is that your regression suffers from the problem of heteroscedasticity.